Hello everyone, welcome back to the NMJ 32004 Integrated Exam Project class. As we promised, today I will introduce to all of you about the complex engineering problem solving. During the project, we will apply all the theories you have learned so far, which will be used and practiced in developing your product or prototype. First of all, you might be asking why complex problem solving or CPS is introduced in your curriculum. The answer is simple. It's crucial. There are many reasons, but I only pick the three most relevant ones. First, accreditation bodies emphasize the importance of complex problem solving skills. These skills are essential for demonstrating our graduates are well prepared to meet the professional standard and expectation in their field. Secondly, CPS equips students to tackle real-world challenges. In today's engineering landscape, problems are rarely straightforward. By mastering CPS, students learn to analyze complex scenarios, consider multiple variables, and develop innovative solutions that can be applied in practice. Lastly, it is important to note that industry expectations are not static. They are evolving. Employers seek graduates who can think critically, adapt to changing conditions, and provide effective solutions to complex issues. By incorporating CPS in our curriculum, we ensure that our students are not only employable, but also valuable contributors to their organization. Before we move on, let's take a moment to watch a video that highlights the real-world application of CPS, a concept that engineers have embraced for centuries. This video will delve into the fascinating history of bicycles.
There was a design problem in early bicycles. It was difficult to get them to move at high speeds. Sure, you could crank the pedals faster and faster, but after a while, it was hard to move your feet that quickly, especially if your pedals are attached directly to the wheel you're trying to steer. Before engineers incorporated gears into bikes, they were limited to each turn of the pedals, moving the bike forward one circumference of the wheel. With the pedals on early bikes affixed to the wheel, one 360-degree turn of the pedals could only move you forward a distance of one circumference. A solution came in 1869 when inventors simply made the wheel bigger. Doubling the radius of the wheel creates a circumference twice as long, which would propel you forward twice as far for every wheel rotation. This kind of bicycle, called a high wheel or penny farthing, could travel at higher speeds and became more popular than the previous bicycles, which were nicknamed bone shakers. The traditional bikes were particularly uncomfortable to ride on uneven surfaces. If you hit a bump with the front of your wheel, you would get a sharp jolt. However, the high wheel was also better in this respect. The larger the wheel, the softer the angle it will have when hitting a bump. So big wheels gave not only a faster, but also a smoother ride. Sure, the high wheel had a higher center of gravity, which meant it was harder to balance. And you had a longer distance to fall and obtain injuries. But as long as you could move fast enough and look cool, that apparently didn't matter. When bicycles were first invented, there was a challenge in designing them to move quickly without having to crank the pedals so fast. That problem was initially solved by taking the wheel that was being turned and making it extra large. However, this method gave speed at the expense of stability and safety. A better solution came by using a mechanism that had actually been around for thousands of years: gears. This solution was right in front of everyone's face, considering this was happening around the time of the Industrial Revolution in Europe, which was being powered by machines full of gears. One set of interlocking teeth on a circle push a set on another circle. If the gears are the same size, one gear will push the other at the same rotational speed. But we can change the size of the gears. For example, if we triple the size of the gear being driven, the two will no longer rotate at the same speed. It would take 3 rotations of the smaller driving gear to turn the larger gear one time. the rotation of the second gear is slowed down. If we reverse the gear sizes, we see the opposite effect. Now, one turn of the driving gear spins the smaller gear 3 times, and we speed up the rotation. So, different gear sizes could be a way to move bicycle wheels faster without having to crank a pedal so quickly. And the driven wheel could be the back wheel to help free up the front wheel for steering. But using 2 directly connected gears wouldn't exactly work. When one gear turns another, the rotation is reversed, so pedaling forwards would drive the bicycle backwards. The fix would have to come from another centuries-old invention, the chain drive. In 1092, the Chinese scholar Su Song was designing an astronomy tower with a clock mechanism to help track the movement of the night sky. To drive the exacting rotation needed in a clock, he developed a chain mechanism to move gears that were offset from each other. Chains similar to those we see in bikes today were sketched by Leonardo da Vinci in the 16th century. These chains could wrap around special gears called sprockets. With the chain drive connecting different sized sprockets, you could still have different rotational speeds, but at a distance and in the same direction. Having a larger sprocket at the pedals, drive a chain that turns a smaller sprocket affixed to the back wheel would allow the bike to move faster with slower pedaling. So far, we've seen how the design of early bicycles was focused on getting them to move faster without having to crank the pedals as quickly. The solution came with a chain driving different sized gears or sprockets. If one sprocket drives another of the same size, they turn at the same speed. But if a sprocket turns a smaller one, the smaller one will turn faster. For example, if the smaller sprocket has 1/3 the circumference, it will rotate 3 times as fast. But turning the wheels as fast as possible isn't always the goal. If you aren't already moving quickly, a chain that turns the wheel faster could create overly hard work. Each rotation of the wheels sends the bike forward a distance of 1 circumference. If one turn of the pedals is geared to send you forward 3 wheel circumferences, and you are starting from a dead stop, that would be 1 hard turn of the pedals to make. Sometimes what is needed is more torque, the force to get something to rotate. If the bike is starting from a stop, or moving uphill, it's harder to get the wheels to rotate, and more torque is needed. But supplying torque comes at the expense of speed. Consider this: if you have a wrench and are trying to loosen a tight bolt, it's going to be harder to move it with a short wrench. A longer wrench is going to give you more leverage to move the bolt. A quarter turn of a long wrench means you're able to distribute your effort over a much longer distance to turn the bolt 90 degrees. With a shorter wrench, you have to compress all that work into a much shorter distance, making the work harder. The longer wrench may make it easier to do the work of loosening a tight bolt, but it comes at the expense of speed. If the bolt is loose and you want to turn it quickly, the long wrench gives you an expanded circumference around. Moving a few inches around with a long wrench turns the bolt less than the same distance covered by the short wrench, making the short wrench the better choice for faster speeds. If we apply this principle to the sprockets in our bike, turning a small sprocket would be a good choice for moving the bike quickly. But if we are starting from a stop, or going uphill and need more torque, it would be better to turn a larger sprocket. In order to satisfy both situations, the initial solution was to put a small sprocket on one side of the rear wheel and a bigger sprocket on the other side. The rider could be speeding along with the chain drive on the small sprocket, and when they came to a hill and needed more torque, they could just stop, detach the rear wheel, flip it around, reattach it, and affix the chain to the larger sprocket. This may not be the most elegant solution, but it did work. Starting in 1895 with the first multi-gear chain-driven bicycle, there quickly came literally hundreds of patents for systems to switch gearing on bikes called derailleurs. They featured different lever systems to switch or derail the chain from one sprocket to another while maintaining tension in the chain. These designs progressed over time to become more reliable and sturdy. However, these derailleurs were not initially accepted by the newly formed bicycle racing organizations. Switching gears without having to stop, remove, and reattach the wheel was seen as a cheat. This might not be surprising, considering how initially riders and racing organizations didn't even want the geared wheel to be on a ratchet mechanism, allowing it to spin freely going downhill. It was a better testament of skill to force your pedals to whirl around madly as you sped downhill. But eventually, in 1937, the Tour de France allowed all riders to compete with a standard derailleur bicycle manufactured by the cyclist and bicycle developer Oscar Egg. His bicycle would help pave the way for future innovations in bicycle gearing, and would prove to be even more useful than the design of his aerodynamic butt cone.
This is the summary of bicycle evolution over the centuries, starting in 1917, when it was initially developed by Dreisel, two-wheelers without pedals, till the modern 19th century carbon fiber frame for lighter, stronger, and aerodynamic design. Now we have explored the evolution of bicycle design from 1817 to the innovative carbon fiber body in 1990s. It is clear that engineering challenges have become increasingly complex over time. This progression highlights the necessity for a robust approach to problem solving in engineering. To effectively address the complexity, we can rely on the three important frameworks of complex problem solving. The first one is the knowledge profile or WK. WK encompasses the essential information, skill, and expertise needed to understand and tackle engineering problems. This framework enables students to establish a solid foundation of knowledge, which is essential for informed decision making. The second one is problem solving, WP. WP focus on the methodologies and strategies to analyze and approach complex problems. This include defining the problem, generating solution, and evaluating outcomes, ensuring the student can navigate real-world challenges effectively. And the last one is the engineering activities. Engineering activities which involve applying theoretical knowledge and problem-solving skill in the practical context. This framework encourages hands-on experience and collaborative work, enabling students to engage with the real-world engineering tasks and think critically about solutions. As we discuss this framework, keep in mind that how they interconnect and support one another in developing effective complex problem solving in engineering. Now, let's explore the 8 knowledge profile critical for our understanding of complex problem solving in engineering. Each profile represents a key area of knowledge essential for effective practice in the discipline. WK1 Natural Sciences, a systematic theory-based understanding of the natural science applicable to engineering. WK2 Mathematics, conceptually based mathematics, numerical analysis, statistics, and computer science to support analysis and modeling. WK3 Engineering Fundamentals, the systematic formulation of engineering fundamentals required in the discipline. WK4 Specialist Knowledge, Engineering Specialist Knowledge, providing theoretical frameworks for accepted practice areas. WK5 Engineering Design, knowledge that support engineering design with a specific practice area. WK6 Engineering Knowledge, understanding of the engineering practice and technology in relevant areas of discipline. WK7 Identified Issues, comprehension of the roles of engineering in society, including ethics, public safety, and the impact of engineering activities. WK8 Research Literature, engagement with selected knowledge from the research literature relevant to the discipline. This profile ensures that we have a comprehensive foundation to approach complex engineering challenges effectively. Next, we will examine the problem-solving frameworks essential for tackling complex engineering challenges. Each framework focuses on unique aspects of problem-solving process. WP1, Knowledge Depth. This involves applying engineering fundamentals for first principle analysis. WP2, Conflicting Requirements. Here, we balance technical and non-technical constraints to find viable solutions. WP3, Analysis Depth. This focuses on abstract thinking to drive non-obvious solutions to complex problems. WP4, Novelty. We encourage innovative approaches to address uncommon challenges. WP5, Beyond Standard. The framework extends beyond established practices, pushing the boundaries of conventional engineering. WP6, Stakeholder Complexity. We must manage diverse stakeholders with competing needs to ensure success of the outcome. WP7, System Thinking. Finally, this involves integrating interconnected components and sub-problems to a holistic solution. Together, this framework guide our approach to problem solving in engineering, ensuring we can navigate the complexities of our project effectively. Let us now discuss the engineering activities, EA, crucial for complex problem solving across multiple domains. Each element plays a vital role in our approach. EA1, Range of Resources. We leverage diverse resources, human, financial, equipment, materials, information, and technology to create comprehensive solutions. EA2, Level of Interaction. This involves strategically addressing challenges arising from complex interaction among technical, engineering, and multidisciplinary factors. EA3, Innovation. We apply engineering principles to research in novel contexts, fostering groundbreaking solutions. EA4, Consequences to society and environment. It is essential to consider the significant impact on society and the environment, recognizing the complexity in predicting and mitigating effects on stakeholders and systems. EA5, Familiarity. Finally, we strive to go beyond precedent by applying first principles to navigate uncharted engineering challenges. Together, this activity ensures we address the multifaceted nature of complex engineering problems effectively. By referring back to the evolution timeline of bicycles, we can highlight the knowledge profile (WK), problem-solving frameworks (WP), and engineering activities (EA) at key milestones. For example, in 1970s, the evolution of mountain bikes. At that time, the engineers attempt to develop off-road capability. The related WK, WP, and EA are WK7, Understanding Diverse User Needs, WP6, Off-road versus On-road Requirements, EA4, Environmental Access Implication. This mapping illustrates how this framework converge to drive innovation in bicycle development. Other than the bicycle development itself, let's now examine the evolution of bicycle accessories, which have significantly enhanced safety, comfort, and sustainability in personal transportation. Number one, braking system. Brake have progressed from simple coaster design to powerful hydraulic system, greatly improving stopping safety. Number two, adaptive suspension. Modern suspension systems can automatically adjust to different road surfaces, providing a smoother ride for cyclists. Number three, electric propulsion. Advancement in batteries and smart power control have made electric bikes more efficient and eco-friendly for daily travels. And lastly, future innovation. Looking ahead, bicycles may utilize AI for navigation, self-repairing materials, and solar power to further enhance personal transportation. Moreover, innovation in bicycle technology has also influenced the other vehicles like motorcycle, scooters, and also cars. This evolution underscores the interconnectedness of transportation technologies. Now, let us discuss the evolution of bicycle accessory, particularly braking system, which have greatly enhanced safety and performance. In 1990s, these brakes were introduced to address the challenges of all-weather performance. Here, the engineering problem is to ensure effective stopping in various conditions. The knowledge profiles is to select the advanced materials application in the brake design, and the problem-solving approach was developed using a system integration method, and the related engineering activities is to consider for environmental impact were also crucial. This evolution highlights the innovative solutions that have shaped modern technology, contributing to safer and more reliable riding experience. Now, let's discuss the evolution of bicycle suspension system, which have significantly improved rider comfort and control. Rigid frame. Early bicycles had rigid frames that transmitted all road impacts directly to the rider, resulting in discomfort, especially in rough terrain. Front suspension. The introduction of fork-based suspension system allowed for the absorption of frontal impacts. This innovation enhanced control and reduced rider fatigue, resulting in a more enjoyable ride. Full suspension. The development of full suspension system, which include both front and rear shock absorber, enabled off-road riding. This presented complex engineering challenges, particularly in ensuring effective performance of varied terrains. The advancement reflect the conditioned effort to enhance the cycling experience to innovative engineering solutions. Now, let's explore the critical safety features that enhance the cycling experience. Warning devices. Bicycles have evolved from simple mechanical bell to sophisticated electronic signals. This modern system offers customizable tones and automatic proximity alerts, significantly enhance rider safety in urban environment. Lighting system. The evolution of lighting technology has been revolutionary. We have moved from unreliable oil lamps to self-powered dynamos, culminating in today's energy-efficient LED system. These lights feature smart and adaptive brightness and provide 360-degree visibility, ensuring cyclists are seen from all angles. Lighter and durable body. Recent breakthrough in material science have transformed bicycle frames. Today, frames are lightweight, impact resistant, and incorporate high visibility reflective element directly into their structure, further enhance the safety. This advancement collectively improves safety and empower riders on the road. Let's discuss the innovation in folding bicycles that enhance their practicality and convenience. Space saving. Folding bicycles significantly reduce storage footprint, making them ideal for urban living and small spaces. Setup time. Modern quick fold mechanisms have greatly improved, allowing riders to set up bikes in a matter of seconds, enhancing convenience for daily use. Weight reduction. Advancement in material since 1990s have led to lighter frame and components, making folding bicycles easier to carry and maneuver. This innovation make folding bicycle a practical choice for commuters and city dwellers alike. The bicycle evolutionary principle have significantly transformed campus mobility. Today, students have access to a variety of transport options derived from bicycle technology. This includes not only traditional bicycle, but also e-bike, scooters, and even bike sharing program. This innovation promote sustainable transportation, reduce congestion, and enhance connectivity across campus, make it easier for students to navigate their surrounding efficiently. Overall, the integration of bicycle technology into campus mobility supports a greener and more effective lifestyle for all students. By looking at the example of bicycle evolution, you can effectively solve complex problems in your integrated design project. Let's break it down into four key steps. Number one, identify real needs. Understand the core problem before jumping to solution. Just as bicycle designers assesses their riders' needs, they engage with stakeholders to clarify requirements. Number two, research thoroughly. Rather information from multiple resources. Successful bike design come from studying materials and user preferences. Do the same in your IDP by exploring academic and industry insight. Number three, iterate solutions. Develop multiple potential solutions like bicycle prototype, create several concepts, test them, and refine them based on feedback. This process is crucial for determining the most effective approach. And lastly, consider impact. Evaluate wider implications beyond technical performance. Consider sustainability, safety, and social impact to ensure your solution is both relevant and responsible. In conclusion, you can tackle complex challenges in your IDP project like bicycle designers have evolved their craft. Now, let's explore your complex problem-solving journey in the integrated design project. As a guide, the following are the content of CPS, which will be referenced in the meeting minutes. Project kick-off in meeting minutes 1. Start by assembling your diverse team. Each member brings a unique perspective and skill set, making them integral to the success of the project. Conduct a stakeholder analysis to understand their needs and select a compelling project focus that tackle real-world engineering challenges. Development phase, meeting minute 2. In this phase, apply the complex problem-solving framework. Generate innovative solutions using iterative design thinking and assess their technical feasibility. Prototype creation, meeting minute 3. Next, conduct functional prototype. Conduct rigorous testing to validate your solution against established performance requirements and user need. Ensures it meets expectation and requirement. And lastly, final product in meeting minute 4. Finally, refine your design based on testing feedback. Document the engineering process to highlight the value and the impact of your solution, demonstrating its effectiveness. By following these steps, you will successfully navigate the complexities of your IDP project. Remember, you are not alone in this journey. You have support of your team and the resources available to you. You can do this. Now, let's discuss how CPF framework is mapped to our program outcomes. As you can see, not all program outcome or PO are directly mapped with the CPS element. This mapping helps us identify which aspect of our curriculum specifically support the development of complex problem-solving skills. By understanding this connection, we can better focus our effort to enhancing the outcome that are linked to CPS, ensuring that students are well equipped to tackle real-world challenges. Now, let's look the program outcome mapping for the NMJ 32004 Integrated Design Project. This table illustrates PO aligned with WK, WP, and EA elements necessary for developing complex problem-solving competencies. The related PO and CPS framework are PO3, Design or Development of Solution, WK5, Engineering Design, WP1, Depth of Knowledge, WP2, range of conflicting requirement, and WP3, depth of analysis required. PO6, the engineer and society. WK7, societal contact, engineer in society. WP1, depth of knowledge. WP5, extensive applicable codes. WP6, stakeholder involvement and conflicting. PO7, environment and sustainability. WK7, societal contact, environment and sustainability. WP1, depth of knowledge. WP4, familiarity with issue. And WP6, stakeholder involvement and conflicting. PO8, ethics, knowledge profile. WK8, societal context, ethics. PO10, communication, engineering activities. EA3, innovation. EA4, consequences to society and environment. EA5, familiarization with issue. This mapping helps us understand how program outcome contributes to the development of essential skill in integrated design projects. Thank you for your attention today. As you embark on your engineering journey, I encourage you to apply the CPS framework to your own projects. This tool will help you navigate challenges, innovate solutions, and create meaningful impact in your field. Remember, the key steps include identifying real needs, conducting thoroughly research, iterating solution, and evaluating the broader implication of your works. Embrace the principle as you develop your skill and contribute to the engineering community. Thank you again and best of luck of your projects.